Okay, we're going to look at some problems that will help us to review for our Module 2 test. So if we look at this first graph, it says, what symmetry, if any, is there in the graph of f of x equal 2x over x squared minus 4? Now obviously in this example, I have gone ahead and I've graphed this on Desmos, and I've gotten this kind of graph. Now our big choices are going to be x-axis, y-axis, or the origin. So this one is certainly not going to be symmetric to the y-axis, because if I flip it, then this part here would go over here, and there's no graph here. So right away I can say it's not the y-axis. It's not the x-axis, because if it was, this part here flipped over the x-axis would look something like this, but there's no graph there. So this is definitely not symmetric to the x, not symmetric to the y. It does appear to be symmetric to the origin, though, because if it's symmetric to the origin, we're flipping everything over the origin. So this part will kind of match up with this part, and this part flipped over would match up with this part. Now, if I want to verify that algebraically, remember negative x, negative y would give us that. If we plug it in, we should get the original function back. Now, negative y in our case would be the f of x. So we get negative y equal 2 times negative x over negative x squared minus 4. But if I simplify that, that's negative y equal negative 2x over x squared minus 4. And then I have this negative on both sides that I can just cancel the negative and become positive. So it's taking me back to my original. So that's the algebraic check to show that it is symmetric to the origin. But obviously the graph is kind of a good way to go to really verify whether it's symmetric or not. So the second one looks to be a different type of function. We want to know if it's even, odd, or neither. Okay. Now I've again graphed this, but there is an algebraic way to do this as well. So remember, an odd function, if we plug in negative x, we'll get the opposite of the function. And an even function, if we plug in negative x, we should get the original function back out with no negative sign. Okay. We also had the even-odd symmetry theorem, which says odd functions are always symmetric to the origin, like the one above, and even functions are always symmetric to the y-axis. So just looking at the graph, I think it's pretty clear that this is symmetric to the y-axis. So right away I could say this is going to be an even function. If I want to verify it algebraically, I will plug in negative x and see if I get the original function back. So in this case it's h of negative x. So h of negative x is going to be negative x squared minus 1 over negative x to the fourth. But since those are both even powers, even negative signs just disappear. So h of negative x will just be x squared minus 1 over x to the fourth, which just happens to be back to the original, which kind of also verifies that this is an even function. Alright, these next couple of problems seem to be dealing with transformations. So this says, what transformations from the original function, the solid graph, to g of x, the dash graph? So this is my original, and this dash one down here is my new one. So right away I obviously know this is a vertical reflection because it is flipped over. So right away I know it's a vertical reflection because it's flipped over the x-axis. Now the other thing it's going to have to be, of course, if I flip this one, if I flip the original graph, it would look like this, right? Well, obviously that's not going to be enough. I'm going to have to also move it to the left. Looks like 1, 2, 3. So then that was going to be a horizontal shift of 3 units. Shift left of 3. So obviously we're just kind of trying to list the transformations in this one. Just trying to see how the picture moves. In number 4, we're actually going to try to find the equation of this new graph. So we have this original graph, which is y equals absolute value of x. It's obviously an absolute value graph in blue. So we got to see what's happened from the blue graph to the green graph. So the first thing I see is it's been moved up. It appears to be 3 units. But if I move the blue graph up 3, it will look something like this. So there's been some kind of stretch or dilation to this that I have to figure out as well. Now the easiest way to think about that is just think about this point right here. So that point on the graph is 1, 1. That's on my original graph. And this point here appears to be, if I'm not mistaken, it looks like that would be 1, 3.5. Oops. Now we already knew it moved up 3 units because of the shift up. So really it became, if we didn't have a shift, it would be really 1, 0.5. So the dilation, so the vert dilation, in this case it's a vertical compression, is by 0.5. It's basically shrunk down by half. If I move that green line down, you'd see it would be basically half the size as the other one. So if I want to write my equation, it's going to be absolute value of x. There's no horizontal stuff, so nothing inside. I'll put that vertical compression factor of 0.5 here, and then I'll put my shift up of 3 on the outside. Now, of course, you can play with Desmos to figure out what the compression factor is either, but just using these points is a pretty easy way to go. So this last one talks about what transformations have occurred in the equation. G of x equals negative cube root x plus 2 minus 1. So there are 3 things that have changed. So the first thing is that plus 2 on the inside. And I'm always going to start in the inside just to make things easier. So this plus 2 is actually going to be a shift left 2. Remember, it's always the opposite sign, so it's a shift left of 2. Okay? This negative out front, we talked about in the first one, the negative out front is actually the vertical reflection. And then, of course, the negative 1 at the end is going to be a shift down 1. Okay, so question 6 says, what intervals is the function increasing, decreasing? Additionally, state any local maxes or mins. Well, we can see the local mins. Let's just do the local mins first. So the local mins are going to be the point where it goes from decreasing to increasing. So the graph is going down here, so that's a decreasing interval, and then it gets to that bottom point. So my first local min appears to be negative 2.378. comma negative 1.507. The next place where it starts, so then it increases a little bit, so we'll put the increasing in yellow, so there's the increasing. And then it's going to decrease, looks like from that negative 1, 0 all the way down to here, where it's then going to start increasing again. So we have another local min, which would be 2.628, comma negative 20.327. And then, of course, it's going to increase from there to forever. Okay? So our local max, there is a local max where it goes from the opposite, increasing to decreasing, and that appears to be at negative 1, 0. So the local max is at negative 1, 0. So now we have these black intervals that are decreasing and our yellow intervals which are increasing, so we can write those. So this function appears to be increasing. Let's do increasing first. So it's at this little yellow part, but remember, we always just use the x value. So it started from negative 2.378, and then it's going to stop increasing at this local max, which is negative 1. Union, it's also increasing in this last yellow part, which is going to be 2.628 all the way to infinity. So those are the 2 intervals where it appears to be increasing. And there are two black intervals where it's decreasing. And that would be negative infinity to that negative 2.378 union negative 1, and then it appears to be 2.628. And again, make sure when you're doing the increasing and decreasing, you only use the x values. All right, so let's look at question 7, which deals with our inverses that we did in section 2.4. So one way we could graph these and see if the two functions are symmetric to y equals x. I'm just going to test one value just to see if it works, because if it doesn't work, then we can be done. And if it does work, then we can check it, maybe graph them and see if they are symmetric to the line y equals x. So I'm going to pick a random number. I'm going to pick 5. So I'll put in 5 to f. So f of 5 is going to be negative 4 times 5, which is negative 20, plus 5, which is negative 15. So if g was really the inverse, if I plug in negative 15, I should get 5 back out. So let's see what g of negative 15 is. So g of negative 15 would be 4 times negative 15 plus 5, which would be negative 55. So you don't get back what you put in, because in an inverse, remember, whatever you put in the first, if you put the resultant back in the inverse, you should get back where you started. So in this case, we could say f and g are not inverses. Now we also could have graphed it, like I said, seen if it was symmetric. We could have done the composition. I always like to just test one number just to see if it works, because if that doesn't work, then obviously they're not going to be inverses. All right, question 8 says, what is the inverse function of 2x minus over 1 minus 5x? Now to find the inverse of a function, this is where we will switch x and y and resolve for y. So there's no y here, so I'll replace the f of x with y. So this function could be written as y equals 2x over 1 minus 5x. So then to find the inverse, I'm just going to switch that. I'm going to make it x equal to 2y over 1 minus 5y. And then I'm going to use my algebra to try to solve this back for y, and then that answer will be my inverse. So I'm going to multiply both sides by 1 minus 5y, because I always like to get rid of that denominator. So that's going to leave me with x times 1 minus 5y equals just 2y, because these will cancel. So similar to what we did in class, I'll distribute the x, so I get x minus 5xy equals 2y. And now I really want to get the y's by itself, but I have 2y terms. So what I'll do is I'm going to go ahead and I'm going to add the 5xy just to get the terms that both have a y on the same side anyways. So that's going to lead to the equation x, which will still be on the left, equals 2y, which is there, plus now the 5xy. So now if I look at that, these both have a y on the right side, so I'm going to go ahead and factor that y out. So I can factor y out and I'll get 2 plus 5x. And then I'll simply divide both sides by that 2 plus 5x. So y, in this case, is going to be x over 2 plus 5x. And so not only is that y, but what we've just found is we've found f inverse. So this function is our inverse function. So if I were to graph both of those functions on the same grid, they should be symmetric to the line y equals x. Okay, so number 9 says, if the point 2/3 negative 7's on the graph of k of x, name a point that's on k inverse. Well, this is actually pretty simple, because we can just say that if they are inverses, then remember, if xy is on the graph, or on the function, then the point yx is on the inverse. So all we simply have to say is we know negative 7 2/3 is on the inverse. And recall, this is all because they are symmetric to the line y equals x, and so if they're symmetric to that line, they have to be on the inverse. So our last section dealt with this variation, direct variation and inverse variation. So if you recall, direct variations where y equals some number times x, we called it k, and inverse is when it's some number divided by x. So this first problem says y varies directly as x, so that's obviously a key word, this directly, and it says if y is 8 when w is 3, what is the variation equation and what is the value of y when w equals 7? So when I see this word w, or directly, right away I know that means y equals k times, in this case, w. Could be any variable. So y is going to equal some number times w for all y and w. So the goal is to first find what that k is. But I know 8 is y, and I know w is 3. So when y is 8, w is 3. So if I solve that for k, then obviously k is 8/3. So this variation equation, when I plug it back in, we know y will always equal 8/3 times w. So this is true for all x, or L, y, and w. So now the problem says, what is y when w is 7? Well, that's super simple. We just plug in 7. So it's going to be 8/3 times 7. 8/3 times 7 is 56/3. So these problems all work very similar. A lot of people will try to skip from this step all the way to the end, but it's very important that you find the k, you find the equation, and then you plug it in to find your value. Now 11 talks about something that's similar, just a little different, because it has the word, instead of directly, it's going to say indirectly. This could also sometimes say inverse. Well, it says indirectly, so indirectly inverse always mean y equals k divided by, in this case, w. But then the process is very similar. We're going to plug in, we're going to find k, we'll have our equation, so on and so forth. So if I plug in y is 18 when w is 30, I get 18 equals k over 30. So I'll multiply both sides by 30. So 18 times 30 will be 540. So now if I plug that in, my variation equation is going to be y equals 540 divided by w. And now whatever question it asks me is no problem. So this is asking me, what is the value of y when w equals 15? So to find that, I simply will just plug in 15. So y is going to equal 540 divided by 15. 540 divided by 15 is 36. Our last problem on this review is kind of another similar problem with variation, except for it's kind of a word problem situation. But it's really the same, it's a very similar thing. So this says at C, the distance to the horizon is directly proportional to the square root of the elevation. So we have distance, which I'm going to call d, is going to be directly proportional to the square root of elevation. So I'm going to write elevation. I'm going to call it E. Now, interestingly enough, when it says this direct variation, I know it says the distance is directly proportional, so d equals k times, but instead of just E, it's the square root of E. Okay? It could say square, it could say cube, it could say anything. In this case, it just says square root. So now the rest will work pretty similar. We'll find k, we'll plug in, and then we'll find our value. So it says a person who is 36 feet above the water, so that's my elevation. So I'll plug in 36 for my elevation, can see a distance of 7.4 miles. So we have 7.4 equals k times the square root of 36. But the square root of 36 is obviously 6. This is 6k. equals 7.4. So 7.4 divided by 6 is 1.23 repeating. I'll just round to 1.23. So now if I plug that back into my variation equation is going to be D equals 1.23 times the square root of E. And then of course the final part of this problem says, how far can a person see who is 64 feet above the water? So we'll simply plug in 64. So the square root of 64 is 8, so we get 1.23 times 8, which is going to give me 9.84. So this person can see a distance of 9.84 miles. Okay, so hopefully these problems were helpful to you. These are very similar problems that will be on your tests, but of course make sure you study all your notes, all kind of the problems we've done in class, to help prepare yourself.